Good morning. Today we are going to simulate receiving material master data IDOCs from SAP and create corresponding material objects in our TLP platform. To complete this scenario, we are going to use our Job ZILLA module, and we called it like this because it is really a monster. But before we get started, let me give you a brief introduction about Job ZILLA and its components.
The following slide gives us a high-level overview of the Job ZILLA architecture, which is composed mainly of an orchestrator and an executor. The orchestrator is responsible to retrieving jobs that needs to be processed and dispatch them to the available executor nodes. Executor nodes retrieve jobs assigned to them, dispatched to them, and scheduled them for parallel processing. By default, each executor instantiates 10 threads for executing jobs in parallel. Of course, these configurations can be increased or decreased based on the infrastructure. So in an environment like the one that I am showing in this slide, basically the system is capable of processing 30 jobs in parallel. Now, jobs, of course, could be created by receiving messages from external systems. They could be created by internal logic of TLP, or they could even be created periodically at specific intervals. So the typical life cycle of a job is that it gets created, then the orchestrator will dispatch it, then the executor will schedule it, and then execute it. Another important concept in Job ZILLA is the concept of queues. A queue represents one or more jobs that must be executed in a chronological order, because their execution depends on each other. Now, why this? This is because maybe business rules of a specific application requires this. If any job could be executed in parallel, then we could avoid using queues. In today's example of material master data, we will assume that the material number represents the queue of received messages, so that if I receive 10 IDOCs of MATMAS for the same material number, we can, having the material number as the queue, we can guarantee that the last received job will be in fact executed as last. So we can guarantee that updates are executed chronologically. Of course, if one job fails in that queue, it will block the execution of successive jobs. Of course, you have possibilities to configure also queues, what we call non-blocking queues, to avoid this behavior. But in general, if we define a queue, it means that we want to block it if something goes wrong. Now, with queues, the orchestrator does the logic of guaranteeing that these jobs are dispatched to a specific node. In fact, you can see that, for example, Q1 was dispatched to node 1, and Q6 was dispatched to node 2. So it's okay to process them in parallel, Q1 and Q6, but the single jobs that belong to that queue must be executed sequentially. Another important aspect in the architecture of Job ZILLA is that it is built on the requirement that TLP is a distributed system, and it is composed of multiple nodes. So whenever a node goes offline, for whatever reason, maintenance, I need to install a new version or whatever. As soon as a node goes down, other nodes of JobZilla knows that they lost one node and act upon that. The possibilities are two. It could happen that one executor node goes down. For example, let's say node 3 goes down. In such case, the orchestrator will take care of redispatching the jobs that were assigned to node 3. If, however, an orchestrator node goes down, which is this situation, so we lost node 1, what happens is that the remaining nodes will communicate with each others and elect a new orchestrator. So in this situation, we can see that node 2 is the new orchestrator, and of course, all jobs that were dispatched to node 1 and not yet processed will be redispatched by the new orchestrator to the available nodes, so to node 2 and 3. So this was a high-level overview of the JobZilla architecture, and in the next section I will give you a hands-on example in which we will receive material master data and process them to better understand the different components of JobZilla.
Okay, so now that the theoretical part is covered, let's take a look at a practical example. I am currently logged in to a TLP environment where I have 3 application servers running, and we have currently the orchestrator is running on app server 1. I have no jobs, so if I click on refresh, I see no jobs. And I also open the applications, the materials application, and we can see that we have no materials in the system. As first test, what I will do is I will simulate receiving one MATMAS from SAP. To do so, we created a simple, I prepared a simple Python script, and let me execute it. Now, as soon as I execute my my Python script, we can see that on app server 1 we got one job that got processed. If I refresh this grid, we can see that one row was created, so one job was created, and we can take a look at, for example, if I click on the ID, I can see the IDOC that I received. In this IDOC, we can see that we can see the material number, the unit of measure, and, for example, the description of the material. So processing this job for sure caused the creation of a material. So if I refresh on the materials application, we can see that now we have one material in the system. Some interesting information are, for example, the columns PT and LT. PT stands for the processing time. In this case, it's 18 milliseconds, while LT stands for the lead time, which is the time since the job is created until it is processed. So, as we saw before, the job is first created, then it is dispatched, and then processed. So the lead time takes in consideration all this time. Now, to better understand what happens by JobZilla under the hoods, what I will do is I will stop the orchestrator, the poller, and the executor. So basically, I am putting the system in a situation, in a condition where it can receive jobs, but these jobs will only be created. They will not be dispatched nor processed. So, and then I will start them step by step to see what happens. And I will also generate this time 200 MATMAS messages. So this script is done. So 200 jobs were communicated. We can see it by refreshing this grid. So we can see that we have many jobs that are in status created, but not yet processed. And if I go to the jobs by status, we can see that now we have 200 jobs in status created. Now, as we said, the orchestrator is responsible to dispatching jobs to the different application nodes. So as soon as I start the orchestrator, we can see that jobs change status and they are moved from the created to the dispatched status. But how did they get dispatched? As you can see, the system, the orchestrator, distributed the load of jobs to the different available executor nodes. So basically, each application server received 1/3 of these 200. So we have 67, 67, and 66 jobs. Now, as soon as I start the poller will get the dispatched jobs and schedule them for execution. So as you can see, the jobs moved from the dispatched status to the scheduled status. And finally, as I enable the executors, jobs will start getting processed and we are done. As you can see, the processing is very, very fast. Now, if I refresh here, we can see that all jobs got processed. And if I go to the materials and I refresh, we can see that now we have many materials in the system. In total, 201 materials. Now, let's do another example. And let me stop again the different modules of Job ZILLA, and let me start third script, which is a script that generates multiple jobs, but this time these jobs are for the same material number, which means that these jobs will share the same queue. So let's create them. Here we are. So we have 10 messages, all for the same material. So if I refresh here, let me show you also here. So we have the 10 jobs created, and we can see that now we have all these jobs have the same queue, which is 9, couple of zeros, and then 1. What is interesting in these jobs that we forced an error that will happen at the 4th job. So if I take a look at it, you can see that the unit of measure is XX, which is a unit of measure that does not exist in TLP. So this job will fail. It will not be processed. Now, when jobs have the same queue, the requirement is that jobs must be the Job ZILLA must guarantee that jobs are processed in sequence and respecting the time in which they were received. And since the job number 4 will fail, basically the queue will be blocked and successive jobs will not be processed. Now, first step is let's start the orchestrator, and what we can notice is that in order to guarantee this sequentiality, the orchestrator dispatched all jobs on the same node, and it did not distribute them because they all belong to the same queue. Now, let me start polling and execution. As you can see, now of the 10 jobs, 4 were processed, but 1 failed. So the last 6 jobs are scheduled but not processed. We can see it also here. So if I refresh, we can see that we have 1 job that failed because of the non-existing unit of measure, and this failure blocked the queue of this material. So next jobs are not processed. Now, in this situation, it's either we either need to fix the problem in TLP, or maybe we really received a wrong message, and it means that this job it's safe to archive it. In our situation, let's say that indeed the unit of measure XX is wrong, it does not exist. So what I will do is archive the job. Now, as soon as we archive the job, basically we will unblock the queue so that next jobs can be processed. Let's confirm. Here we are, and as you can see, there are no more scheduled jobs, and if I refresh here, we got the rest of our jobs processed. So this is the concept of queues. Of course, for each job type, we need to define what is the correct queue to use, whether we want to block queues or not. So all these decisions are taken when a project is being developed. Okay. Last thing that I wanted to show you about the Job ZILLA module is how it behaves with situations where maybe we are stopping nodes, fault tolerance, and so on. For this scenario, again, I will stop this time the orchestrator and polling and execution. So again, I'm stopping execution, and I will send a little more messages. So this time we will generate 1000 jobs, which are 1000 material master data. We can see the progress here. So we have the number of jobs that are being created. Let's wait until all 1000 jobs are created. Okay, so we got our 1000 jobs. Now, as you can see, nothing is dispatched yet because our orchestrator is off, and the orchestrator is currently running on app server 1. The first thing is that let me simulate shutting down the orchestrator. So I'm stopping the app server 1, and we can observe that in a couple of seconds, app server 1 will not be available anymore, and the system will notice that, and the nodes will elect a new orchestrator. So we can see now that our new orchestrator is app server 2. Let's now start again app server 1, and let me stop app server 2. So again, we expect a change in the orchestrator, and depending on the timing, maybe app server 3 will become the orchestrator, or maybe app server 1. So let's wait until the app server 2 goes totally down. So now it is down. Perfect. And as you can see, now app server 1 is back to being the orchestrator. Let me now bring app server 2 up again. Let's give it a couple of seconds until it starts. Okay, so now we have also app server 2 up and running, and let's start the orchestrator. As we said before, the orchestrator will try to distribute the load on the different available nodes. So as you can see, we got roughly 330 jobs for each node. Now, what happens if I stop one node after jobs were dispatched to it? So let's assume we stop app server 3. Now, when app server 3 is stopped, the system again will detect it, and those jobs that were dispatched to app server 3 will be redispatched by the orchestrator and sent, for example, to app server 1 and app server 2. As you can see now, each node has 500 jobs. So let's start only the poller, and as soon as I execute the poller, jobs are scheduled for execution. And let's assume again that app server 1 goes down. Now, basically, since app server 1 goes down, those 500 jobs assigned to app server 1 should be redispatched and rescheduled to the last available node, which is app server 2. Let's give it a couple of seconds to see what happens. And as you can see, now we have all 1000 jobs scheduled on app server 2. So this shows you how the Job ZILLA architecture is resilient to possible stoppages or downtimes of specific nodes. Now let's start execution and let's see how fast jobs are being processed. As you can see, in less of 15 seconds, all 1000 jobs will be executed and materials will be created. So we got all our jobs processed, and if I go to my materials and I refresh, we can see that now we have 1202 materials. So this is our Job ZILLA module. As said, it can be used to manage communication with or from external systems. It could be used to create periodic tasks in the system, or anything that you want to execute in an asynchronous way. Then it can be converted to a job and processed as a job. Thank you very much.